So today what we're going to do is we're going to look at how much energy it takes to either melt a substance or freeze a substance. So far we've dealt with heating and cooling a substance that stays within its phase. And when you do that, you get a delta T. So if I have a temperature change, I can always plug it into the formula Q equals the mass times the temperature change times the specific heat. What happens during the freezing and the melting, though, or any phase change, condensation, vaporization, is you don't have a temperature change. So if I were to plug zero, the temperature change of zero in here, I would get that no energy is required to melt something, but you know that that's not true. So what we're going to do is we're going to use something called the heat of fusion. The heat of fusion for water happens to be 334 joules per gram. So 334 joules is required to melt 1 gram of a substance. So heat of fusion is defined as the amount of energy required to either melt 1 gram of a substance that's already at its melting point, or the energy needed to be removed in order to freeze 1 gram of a substance that's already at its freezing point. The key is that there can't be any temperature change anymore, so that's why it has to be at its melting point or freezing point already. We can't have any temperature change. All right, so next thing we're going to do is we're going to try a problem with it. So we're dealing with this phase change. Remember, there's no temperature change, so what formula am I going to use? Formula changes a little bit. It's Q equals mass now times the heat of fusion. That's the new constant that we just learned. Notice there's no temperature change in here now. So read your questions. It's how much energy is required to melt 5 grams of a substance whose temperature is at 0. Now that's important because that tells us that this ice heated up, got all the way over to the point at which it's ready to melt. And now I can calculate how much energy. I don't have any delta T anymore. So given this as our formula, I know that I've got 5.0 grams of ice. I know that it requires 334 joules to melt every gram of that ice. Don't forget to put your units in. The grams will cancel. You know you set it up right. And now 5 times the 334 is going to be 1,670 joules of energy. Two significant figures because this is our measured value over here. Always use your measured values. And you're going to end up with 1,700 joules are required to melt those 5 grams of ice. Try a different one. This time, we're going to try cooling a water down, getting to its temperature of 0 degrees. How much energy needs to be removed in order to take that liquid to the solid phase? So I'm going to go from the liquid to the solid phase. How much energy needs to be removed to freeze 25 grams of water? It's important that it's water, so I know I'm using the right heat of fusion whose temperature is at 0 degrees Celsius. So again, I know my formula is Q equals the mass times the heat of fusion. I know that there's 25.0 grams of water. I also know from the previous slide that 334 joules is required to melt or needs to be removed, so exothermic, to freeze this water. So 25 times 334 gives you negative 8,350 joules of energy. So that's the amount of energy, 3 significant figures, that's the amount of energy that has to be removed. Notice exothermic because we're removing the energy in order to freeze and form those intermolecular attractions. What happens, though, if we're up here on the upper plateau, where we're either vaporizing or condensing a substance, going from the liquid to the gas or from the gas to the liquid phase? Then what do? Well, heat of vaporization for water is 2,260 joules per gram, and it's the amount of energy required to either evaporate 1 gram of a substance at, it has to be at its boiling point. For water, it would have to be at 100. And the amount of energy needed to remove, to condense 1 gram of a substance at, again, it has to be at its boiling point. Okay? So, heat of vaporization for water is 2,260 joules per gram. You have to remove a lot of energy to get it to condense, or you have to add a lot in order to get the water to separate and go into the gas phase. Let's try some problems. The formula for this upper plateau is very similar to the bottom one. No temperature change again. Q equals mass times the heat of vaporization. I use heat of vaporization anytime I'm dealing with the gas phase, either going to the gas phase or coming from it. I'm going to use the heat of vaporization. How much energy must be removed to condense 15 grams of steam whose temperature is at 100. Important that I'm at 100 because that's where the phase change takes place, so I don't have a delta T. All right, so formula is Q equals mass times the heat of vaporization. What do I know? I know my mass. My mass is 15.0 grams. I do know my heat of vaporization is 2,260 joules for every 1 gram. The grams are going to cancel. One's in the numerator, one's in the denominator, and you get a total of 33,900 that needs to be removed. Now, since it needs to be removed, this is a negative value since it's exothermic, so you can say that Q is negative 33,900 joules. And I'll answer that amount of energy that needs to be removed from 15 grams of steam in order to get it to condense back into the liquid phase. Try one more. This one's a little bit different. Again, I'm dealing with the gas phase. I'm dealing with evaporation. But let's look at this problem. It says a sample of water at 100 degrees Celsius, good, I'm already there, no delta T, absorbs 24,200 joules of energy. Well, that's my Q this time. This time I'm telling you how much energy it absorbs. And I want to know how much water is in the sample. So I'm looking for M. The mass is my X. I know the formula. Q equals mass times the heat of vaporization. So what happens is I plug it in, 24,200 joules. That's the amount of energy that I know was absorbed by the sample. I don't know how much mass, but I do know that for every gram, 2,260 required in order to evaporate that substance. Solve for X. What's going to happen is you're going to divide both sides by the 2,260 joules. And when I do that, divide both sides by 2,200 oh, no, I was right, 2,260 joules per gram. 2,260 joules per gram. Cancel out. Here, the joules cancel out. The grams are actually going to end up on the top because it's a reciprocal, but it's on the bottom. So we end up with a nice mass. X is our mass of 10.7 grams. 10.7 grams is your mass. So it's not always Q that you're solving for. One last slide. Heat of fusion and heat of vaporization are both intensive properties of a substance. The heat of fusion, for example, for water is 334 joules per gram. Heat of fusion for hexane is 151 joules per gram. So here's my water molecule, and here's my hexane molecule. So why would the heat of fusion of water be so much higher than the heat of fusion for hexane? Why might that be? Think about that. We're going to start class tomorrow with that question. Have a great night, you guys.